Welcome to the Val Studio. Today I'm going to be talking about distortion, harmonic and intermodulation distortion. And I'm going to introduce a tool I developed called the Imd Explorer. And with it, you can create single frequencies, two frequencies, three frequencies, and you can also change characteristics of a gain stage. You can have a linear one, you can have a clipped linear one, or you can have something that's akin to a tube amplifier. For both a Pentode and for a Triode. We'll go ahead and get into that, and I will show you a few papers that was the reason why I came up with this tool. And primarily I'm working on an amplifier here, and I'm thinking about using Pentodes for the preamp stage. And where do you pick the screen voltage? Where do you put the bias point? What's the what does it mean to use a Pentode for that? I found three papers and that kind of go into this a little bit, but I needed this tool to actually explore this further. So we will go talk about the papers first. First one I found, actually after a lot of digging, I found this one. This is an original document from Terman and Hewlett. Hewlett is HP fame, and Terman is a Stanford professor, I believe. This is from 1940, and this talks about at a collegiate level how to use Pentodes for voltage amplifiers. This one is fairly difficult to read, but an easier one is this one called Dynamic Characteristics of Pentodes. This is a 2-spread out of a magazine. This from Communications of July 1946, and this talks a lot about choosing different screen voltages as well as plate resistors itself, and what that actually does to the characteristics of it. And this is a curve that you don't often see in a data sheet. This is a dynamic characteristic that shows you the plate voltage versus the screen voltage, and also versus the grid voltage. And if a big question is when you're designing with Pentodes, what do you actually choose the screen voltage to be? And by choosing it, you get to pick which one of these curves you're going to reside on, and by changing the bias point, you can change basically where on an individual curve you actually have your signal traverse. And we'll show you that. This is the whole reason why I came up with the Imd Explorer tool. There's another paper here from Radiotronics, July 1948. And this one is, this is the theory section from Langford-Smith. Langford-Smith, the author of a Radio Designer's Handbook, known as the Bible. RDH4 is the one I have. And down here, he talks about intermodulation distortion. There's not much covered on intermodulation distortion. If you're designing an amplifier, audio amplifier, you want to minimize the IMD, the intermodulation distortion. But if you're designing a guitar amplifier, you can take advantage of that and tailor the sound, the actual distortion characteristics of your amplifier to enhance the guitar itself. So there's two different kind of camps here. We can actually look at both of those at the same time, and I will go ahead and show you why a distortion pedal sounds like crap when you play 3 or more notes on it, because you take those 3 notes and it will become hundreds of different notes, and we'll show you that in just a minute. And let me see, if you want to download this, you can go to the My Val Studio GitHub page, and it is under Projects, Pentode Operating Point, Source, Baby Steps, and it is called the Imd Explorer. It's just a straight Python code. You don't have to get Jupyter Notebook running. You just run it right from the command line. It uses matplotlib for an interactive session. And one last thing is, if you're designing guitar amplifiers and you want to learn about why they sound better, then we'll talk a lot about that here today. But there's a complete paper from Rutt that was in the Audio Engineering Society that talks about this specifically, and how the soft limiting of tubes creates more pleasing tonal characteristics than the hard clipping limit for transistors itself. And it goes into here telling exactly why you can't mimic a tube characteristic with a transistor. All right, let's bring up the tool. I have it running here. It's got 4 main windows, 4 main graphs. The top left graph is our combination of 3 input frequencies. And let me check things here. Okay, I think all right, we're still going. So you can, like I said, you can have a combination of 1, 2, or 3 frequencies going into our amplifier. This one here is an input-output section, and it's going to show you the input waveform that you create over here, as well as the output waveform after the amplification stage. This window down here is showing you what the amplification transfer curve looks like. We're currently on the linear setting, so we have a straight linear line, and that produces no distortion whatsoever. You can see that over here in our spectral output. This is just basically taking an FFT of the output voltage up here. Down here we can control the frequency, amplitude, and phase of each of our input frequencies. And I can go ahead and show you that, but I'm going to change the frequency of our number 1 oscillator, and you can see that we're getting more cycles here as well as here, and our output frequency in this over in the spectrum is at 781. It also tells you what the frequency is up here. All right, so if we move around here, we'll just basically move in the position of our peak, and I can also change the level. I can increase and decrease the level of these signals going into the amplifier. And you can, this graph auto scales, so if you were to look at it, you can kind of see that our blue wave, which is the VN, stays the same, but it really is getting larger, but the output waveform is setting the scale of that graph up there. And you can also see down here, this is our gain stage. We can change the characteristic of that gain stage by changing the gain slider here, which effectively changes the slope of this linear amplifier. And we'll talk a little bit about the bias in a minute. There's some equations up here that kind of tell you what's going on if you're running in clean, or in linear or not linear. Over here is some radio buttons that allow you to hit some preset values. I have 300. I have 300 and 400, so if you can kind of click on that. It basically sets all these sliders down here to be a preset value. 300 and 400 is something that is an important way to actually look at intermodulation distortion. And I learned about that by reading this last paper from Cohen, which is talking about the Cohen 3-4 ratio. And it is a way to actually understand intermodulation distortion. We'll talk a lot about that in when we get further along in our demo. But for now, let's go back to a 300 hertz waveform. This last thing is down here, this last radio button down here is actually a button. If you hit this, it'll actually play on the audio speakers here. So that's our 300 hertz waveform going in. And if I do 300 and 400, you'll hear 2 frequencies here. If you're old school like me, you actually know what touch tones are, and this is the reason why. This is the core thing about how touch tones work, is they actually use 2 different frequencies to set up the matrix for the on a telephone. All right, let's go back to a simple amplifier here, 300 hertz or linear. Now, if you go here down here and you hit on the clip thing, what we're actually doing is we're introducing a hard clipping region at plus and minus 50 volts, and this would be your power supply voltage on the output stage on a power amplifier that uses transistors, because we're going to have limitations there on what that is. And we're operating in a linear region here. We have not crossed over the clipping itself, because you can kind of see in our spectrum we still only have one frequency. I'm going to change the gain just a little bit, and we'll cross over those transitions points here, and you'll actually see that our single one frequency now becomes hundreds of I'm just going to gently cross over there, so you can't really see it over here. You barely see it's crossed over, but just a small increment in amplitude going into our amplifier now results in 72 peaks over our spectrum. Now this one here, if you look at this frequency, this amplitude, this is probably 30 dB, and this one is down at minus 10, so it's 40 dB difference. That's still audible. We'll go ahead and play that here. Okay, so we have you can kind of hear that we are getting a little bit distortion. I can turn that back down again, and I'll go ahead and show you about this offset. This offset actually changes the region at which the signal goes into the amplifier. You can kind of see that I'm effectively changing the offset going into the amplifier. And as long as I stay in the linear region, we're good. We don't get any intermodulation distortion. We don't get any harmonic distortion. But if I were to cross over one of those boundaries, I'm going to now introduce a bunch more distortion. And it's that sharp transition there. If you look up here on our output waveform, you can kind of see that we are clipped on the high side. I'll go ahead and move the offset down, so we're now clipping on the low side, which is what's going on over here. It's these sharp transitions right here that create all those harmonics. So we'll just play this one here. It does sound a little bit different, but this isn't, we're doing valves, man. We're not going to do transistors here, but I wanted to show you what the impact of a hard clipping is on the amount of harmonics that gets generated. And this becomes a tremendous source of frequencies if we actually start using multiple notes. We'll go into that in just a minute. We'll click down here to bias 0, which brings up a similar type of curve. If you remember from these curves here, this is the Pentode characteristic that's showing you the plate voltage versus the grid voltage and the plate current. Not the plate current, and the screen voltage and the grid voltage. And you can move those back and forth. We can do that exact same thing over in the Explorer by changing this thing here called the bias. We can change bias, and we can also change the overall gain, which is the height of our waveform. And the bias actually ends up changing the slope at which that arctangent function actually changes. So here is this is somewhat representative of the middle of a Pentode. We have a single 300 hertz waveform going in, and we are symmetric about the origin. So a characteristic of this type of distortion, where you have equal distortion properties on both sides of the waveform, creates odd harmonics. And we can see that over here this is now showing you the frequencies that we are 300 hertz, which is, this is our main frequency up here. And we're at 900, that's the third harmonic, and we're at 1500, that's the fifth. So go and play that. All right, so at this amplitude level, going into our amplifier, it looks like we're in the linear region, but we're actually not, and we're starting to see a little bit of harmonic distortion. And in this case, this is the odd harmonics. Okay, so there's a characteristic where if you don't have symmetry about an origin, where your waveform is actually shaped different on the top half than the bottom half, you end up with even harmonics. We can show that by setting the offset over here of our waveform, and we kick it off the center, and you can't really tell yet, but the top waveform up there, the tops look a little bit different than the bottom, and you'll see that now our primary harmonic is now a second, which is at 600 hertz. We still have a little bit of third. Now we have a fourth, but our fifth harmonic is way down. So let's take a listen to what that sounds like. So musically, if you're playing a single frequency and you get doubles, oh, I got a dog barking. You get doubles, double the frequency as well as fourths. That's pleasing to our ear, where the third and the fifth are actually a little bit harsh. All right, so that's harmonic distortion, and we have 6 peaks right here for our amplifier set at this point. And let's talk about intermodulation distortion now. Intermodulation distortion comes up, and the Cohen wrote this paper called the 3-4 ratio. This is from 2008. This is a guy from Australia, and he talks about choosing your frequencies such that they are not 100 and 200 or something like that, but there's a nice characteristic of choosing a 3 and a 4, whether you're at 30 hertz and 40 hertz, 300 and 400, 3000, 4000, 3 megahertz, 4 megahertz, whatever it is. There's the way that the intermodulation frequencies are generated are very easy to find in the spectrum. So we'll come down here and he'll show you this. So here, now let's talk about the harmonics. So the harmonics itself are shown in this table down here. So here's our 3, and we're at F1 is a 3. So this is our 2 fundamentals. And the second harmonic of our fundamental is going to be at 6. So we have a 2F here, which is our second harmonic. All right, and then we have the 4 here, so we're going to have the second harmonic at 8 over here, which is the second harmonic of F2. All right, and it continues on. Here's the third harmonic, which is the third harmonic of the first fundamental, and so on. You can kind of see where this is going. Now, intermodulation comes about because these frequencies, the main fundamentals and the harmonics of the fundamentals, mix with the fundamental and the harmonics of the other waveform and create some indifference frequencies. And so you can kind of see that we get a 7 here because we're now, this is an addition of the first one and the second one. So we have F1 plus F2, which is 3 plus 7, so we'll get a 7. And then you can kind of see where these are going. Here's 2F1, which is the second of the first fundamental frequency, plus the second one. All right, so by picking 3 and 4, we end up setting up the remaining harmonics as well as the intermodulation harmonics come up on even intervals of 1, basically. And we'll go ahead and show you that over here. So let's go back over to our Explorer. And I will go back to using 3 and 4, which is what he used, and we'll go ahead and go back to linear. So back on linear, we're at 300 and 400, and you can hear it. We'll go ahead and play that with this no distortion because we're on a linear amplifier. Okay, so we played this before. It sounds much like a touch tone. All right, we'll go ahead and turn back on to our tube amplifier. So you can kind of see that we have things here. We're kind of, I'm going to turn the gain down a little bit, and we'll get back to this picture. We should be able to get back to the same kind of picture. So we have 6 on the high side. So if I turn the gain down on this, we can kind of tame those peaks. All right, and we can actually, if you get below 25 peaks, the numbers come back on again. Sorry. So here we are. So we got 3, 4. Here's the 5. We don't have 6, 7, or 8. So let's turn it up a little bit more. All right. So there's 7, and we're not getting any 7 though. I don't know why. But here's 3. Here's 5. 5 is, well, whatever. You can kind of see. We've got 3, 4, 5, 6, 7's down there. It just hadn't come up yet. You can kind of see it right there. It's at minus 90. 8, 9, 1,000, 1,100, 1,200. You can kind of see we're at all these intervals. Now, what's interesting on this graph over here is there's 2 down here, which is a difference frequency of the second minus the primary. So we have a lower frequency, and that's at 200 hertz, and then we still have another one down at 100 hertz. We're seeing that as well down here. So we put in 2 frequencies, and we run it through this nonlinearity of our tune-up amplifier, and at this volume level we get 16 peaks out, including some subharmonics, which are below our fundamentals. Let's go ahead and play that. It sounds very similar because we're at 11 dB up here, and our next highest order one is down at minus 30. So it's a 40 dB change, and that's fairly large. So we're not really contributing that much intermodulation distortion. And if you're to go back and look at this paper here, which is this Radiotronics article, they talk about these choices as well as how to actually come up with these plots of the intermodulation distortion. Again, if you're designing a audio amplifier, you want to minimize that because you don't want all those extra frequencies in there. But if you're doing a guitar amplifier, you may want to go ahead and introduce those, particularly I don't know, you have a choice of that. You can choose the bias point to be in the middle of the curve, or you can choose it up on one or the other side of the curve. Now, let's go back a minute. Okay, so we're taking 2 now. Let's go ahead and turn up our frequency, not our frequency, our amplitude to our signal. So we're getting a fairly we're over here on our transfer curve. We're actually traversing a lot. So I've changed things a lot so that now we're getting 37 peaks out, and we're at 20 and 0. So now we're down 20 dB from our harmonics. So this is going to be a little bit pronounced in terms of frequency. So this is 2 frequencies going in at 300 and 400. Now those just happen to make the sum and difference frequencies be on even intervals. If we were to play a chord, which is what I have over here, this GDG, which is chosen off of guitar chords, this would be the G power chord on the low side. This G here is the low E. So now we have 3 frequencies going in, 196, 294, and 392. And if we play that, we now have 45 peaks. Okay, so we're still not clipping yet. We don't really have any hard clipping up here. Now let's talk a little bit about this hard clipping business. Let's go back to 300, and I'm actually going to introduce another frequency in here. We're going to go back to linear. We're going to change the fundamental to be down to about 100. And then I'm going to dial up the second oscillator up so that it is out here, way out here at about 2000. And then I'm also going to change its amplitude so it's a lot lower. So what you'll see is that we have a high frequency riding on the low frequency, which is what's shown up here. And you can still see that our spectrum only shows two signals. I don't know what this is going to sound like, but all right, so you hear both of them. Now, if we go over here to the bias 0, we've introduced a bunch of more things, but let's turn up the gain here and actually let's go over to clipped. And let's change this gain up so that we are crossing. Wow, look at this. We have 2,000 peaks now. All right, so I've changed the gain up here so that we're hard clipping on the high side and the low side. You can kind of see that we still have the high frequency component in here, but these sharp transitions have now introduced more than 2,000 peaks to this waveform. Well, that doesn't sound anything like what we're doing. But the point of this is I'm going to switch over to the soft limiting, which is our tube amplifier, and I'm going to turn up the gain again so that we get a different kind of character. Our shape of our curve is, we see we're still getting our low signals in here. If you look at the Rutt paper, where's the Rutt paper here? Here we go. Look at the Rutt paper. He goes through a lot, talks about this nonlinearity. He's using a triode, but our examples are still applicable. His conclusion down here at the end of his paper is that the hard clipping, if you read this, I encourage you to read this because this is a very well written paper. There's not hardly any equations in there. It's very easy to understand. He says most solid-state amplifiers have a symmetric brick wall, which we've actually seen, where it limits both sides of the output waveform, which is what we're doing. And this symmetry produces predominantly out-order harmonics, and the hard limiting produces undesirable intermodulation distortion effects, which we are clearly seeing there. But up here he says that soft limiting amplifier lets more of the weak signals through the amplifier even at high signal levels, which is exactly what we're seeing when we go over to our bias, our tube bias, because you can kind of see that we're still getting frequencies through here. Now our intermodulation distortion has created 222 peaks instead of the 2,000 peaks. All right, so now where are we? Let's kind of get crazy here. Let's put in the G major chord, and if we were to use our amplifier at this point, we would now be getting, this is even with soft limiting, we're now getting 3,700 peaks. All right, so you can hear that our waveform that goes in is, well, let's listen to the clean one and we'll come back to that one in a minute. All right, here's the clean one. All right, we turn this gain up here. Okay, so now you can not only hear that we have a lot of frequencies in here, but we also have some motorboating going on, and that's these guys down here, and these low frequencies are actually being introduced into it as well. Now that might be the tone you want. I don't know. We can change also the characteristic of this by shifting the waveform up here, and this is the whole point of this investigation, was if you're designing with a Pentode, what screen voltage do you pick, and where on the curve do you want to actually have your input riding, because you do get to create based on your choice of offset, do get to tailor the output so that you get predominantly second order harmonics. And if you play around with this tool, well, I encourage you to play around with it. It's a lot of fun. It's very fast. I have a pretty fast desktop here, and it draws in near real time. If you're anywhere slower, there's hundreds of calculations going on whenever you move these sliders. And fortunately, this is a pretty fast desktop. But this answers your question about what is intermodulation distortion. How do you minimize it? If you're doing audio amplifiers, you want to, not necessarily stay in the middle of this waveform, which is where all the books say choose the middle, because you're going to get some symmetry there. If you move your bias point off the middle a little bit, you will reduce the odd order harmonics and promote secondary harmonics. I'm going to show you one more thing here. We're going to go back to our 300 and 400 waveform. And over here on the red paper, he goes through and he talks about why you get second harmonics with a tube amplifier and not the third, and primarily the second. It has to do with the soft limiting. He goes through and he basically, that's really the point of this whole paper here, is he's using a simple amplifier, which is a triode with a cathode follower at the output. And he says when you get to the point where you're overdriving this, so on one side you're doing grid limiting, on the other side you're doing plate cutoff. And what ends up happening is that you knock the symmetry out of your waveform, because if you look at this, what you've done is you've shifted the output waveform in a different location, which offsets the symmetry so that the grid limiting is actually wider than the plate cutoff. And by shifting the symmetry, you still have the fundamentals and all that in there, but you introduce a second component as opposed to the third, which is if you had a symmetric waveform. He goes into a lot of detail there. So if you're designing guitar amplifiers, this is a very interesting article that talks about why, why specifically you get desirable characteristics out of a triode, and you can also get additional kind of characteristics out of a pentode based on what you pick the screen voltage to be. All right, well, I encourage you to play around with this. It's a lot of fun. The fact that I got all this done, and I was like, I really like to hear these, so I added this little play button. And this is kind of the key, so you can actually listen to these things. Now, it's not a guitar, but you can kind of see, how well your ear discerns harmonic distortion as well as intermodulation distortion. So this is the reason why when you're playing a power chord on a distortion pedal, it sounds all muddy or washed out or just a bunch of noise, because it is. I mean, if we're playing this G minor, and we're using a distortion clipper, we get 10,000 peaks out of this. So that's why these hard clipping things aren't really a good idea. They probably don't sound. You may want that sound, I don't know, but it's up to you on where you choose your bias points and what you choose your offset going into, what kind of amplifier you want to run into, what kind of linearity you're able to achieve out of your amplifier, whether it's a transistor or a tube amplifier itself. All right, well, thanks for watching. This is the Valve Studio.